Okay, I've started the recording. All right, so today we'll talk about symbolic execution from the theoretical aspect and the research aspect. You've already seen maybe symbolic execution in the TA session and in your assignment, so you should be a bit familiar with the practical side of it, and you might have had some questions about how it works and stuff. And yeah, this is a set of slides prepared by a guy called Fabio Gritti. He's part of the Shellfish team. I think he worked on Anger as well, because yeah, Shellfish made Anger. And I've adapted these slides a bit for this lecture, just shortened some parts, edited some parts. So it shouldn't be too different, but yeah, the credit goes to him for preparing it. Yeah. So bug hunting is basically looking for unexpected behavior in programs, and that can range from all the way from logic bugs and semantic bugs to invalid memory accesses and stuff like that. So and it can be very let's say precious for you to find these bugs in software, either for you as a developer because you want to improve your product, or as an attacker because you want to make some money on the black market. So yeah, each hunter has different motivations and may use different tools. And in this lecture, we'll talk a bit about symbolic execution for bug hunting and how we can leverage that kind of abstract interpretation of programs to find bugs in them. So a typical question you can ask is, like, you have some function, right? And you have the arguments that the function takes. And you have some assertion which you as a programmer wrote because you say, okay, this is what should be at all times regardless of what the arguments are sent. And you want to see, is there a value for the arguments that violates this assertion? And you can go through it, maybe line by line, and say, okay, yeah, if I have y equals whatever, and then if b equals 0, but what if b is not equal to 0? And then eventually, for all the cases, you find or for all the paths, let's say, through the program, you find something that either violates or never violates the assertion. But there's a systematic way to do it. That's called symbolic execution. And basically, yeah, it treats A and B as symbolic variables, which we talked about a bit in the TA session, which means they don't have any concrete value. They're just variables that hold some value, and then as you proceed through the program, you add some constraints on those values, depending on which path you take. So if you take the through path in the if statement, if a not equal to 0, then you step into the then statement, and then your first constraint on a is that a is never equal to 0. Now, systematically, you would say, okay, what if it is equal to 0? Then you step out of the then statement into the else, but here there's no else, so you just step into the assert. And there, the constraint is that a is equal to 0. And then so on and so forth. For every time you pass through a statement, you add the constraints of that statement onto your path. And then eventually, if you pass this to a symbolic execution engine, it will tell you, yeah, for a equals 2 and b equals 0, this violates the assertion. And you found a bug. So yeah. All right. So a program binary is typically what we consider a program binary is just a compiled source code, right? Like, you get the source code which was written by a developer, and then you compile it into machine code, you double click it, you run it in the bash, whatever, it executes, and then that's it. That's a program binary. But from a more abstract or a less strict definition, you can look at a program binary as just a set of instructions for some machine that can interpret those instructions. And this can also be seen in languages like Python, where the lines are interpreted by the interpreter. They're compiled to let's say bytecode, and the bytecode is executed by the interpreter, and it never in a sense, the script that you write is never compiled to machine code that runs on your x86 processor. It's compiled into the bytecode, and then the bytecode is interpreted by the interpreter, which is in itself compiled as machine code. But the interpreter is the one still doing the execution, so it is the one running it. So it is the execution engine. And if we look at it from that perspective, then okay, we can say that a symbolic executor, which we'll see later, is in itself the execution engine. It just has a bit different semantics. Like instead of executing in one path as you would expect usually from any executor or concrete executor, it executes all paths of the program, and that allows it to do what it claims to be able to do. But in a sense, it is still executing the program, but just in all directions. All right. So yeah, we can use symbolic execution to explore all paths in the program, and then through those paths we can find some violations that we depict as or that we consider as bugs. However, or not however, but like one good thing for using symbolic execution for bug hunting is that we're not using it to verify the correctness of the program or to verify that there exists no bugs in the program. We can use it to prove that a bug does exist in the program, if we're looking for that bug. And that makes it a bit easier, because usually just verifying correctness is a hard problem and requires a lot of formal proofs and whatnot. But with bug hunting, you just have to find one, and that is usually sound. And then, we find one proof of concept, and that means that the bug exists. And that makes it a looser definition or a looser constraint on symbolic execution for bug hunting, rather than proving the correctness of the whole program. All right. So why are we dealing with binaries? Why don't we do this at the source code level? Because when you have binaries, let's say in some assembly language, x86, whatever, this makes it independent of the source language. If you want to do it at the source language level, each source language has its own semantics. It might be too complex, and you have many programming languages. So if you want to implement a symbolic executor for a language, you're going to do it for only that one language. It's going to be difficult for you to implement it for all languages, because you'll have to add basically the translation layer, let's say, for all languages, or some other, I don't know. It's going to be difficult. So with binaries, you just have this common language that runs most commonly on these assembly at the assembly level, and and we can see later that even if you have different assemblies, usually you can lift them into a better, let's not say better, a universal intermediate representation which the symbolic execution operates on. So you don't even have to support all, let's say, assembly languages. You just have to have a lifter that does it for you, and then after you lift it to that intermediate representation, which is like we discussed here, like the symbolic executor can then interpret the intermediate representation, and then it would it would be able to do its job as it would do for any other assembly language. And another reason is that truth lies in the binary. Now here I referenced I referenced a tweet by, like, it's a recent tweet for a bug in the GCC compiler. It exists in the latest version, and like if you look at the code and you look at the assembly, they're nothing alike. It's just like, wait, where did all those checks go? It just assumed everything and then it just returned 1. It's wrong. So if you do it at the source code level, you wouldn't have found that bug. But in the end, what really executes is the binary. So, and if you look at the binary, there was the bug in the binary, not in the source code. It was a compiler bug, of course, but if you're in production, you want to test if your product has bugs. You want to see what your producing, what you're shipping, rather than what you think you're shipping. And then sometimes source code is not available in some domains, like malware analysis stuff. Am I recording? Yeah. Okay. So why do we do symbolic analysis? Now we looked at why we do binaries, and now why symbolic analysis? So this allows you, symbolic execution allows you to explore a program's behavior systematically, or program set of behaviors systematically. So you want to know which code is triggered by which input. You can, like, let's say, see all the paths that reach that code, trace them back to the constraints on the input, and you know which inputs trigger which code, or vice versa. You can also prove that there exists no input for which the program reaches a specific state. So basically, this is the unsatisfiability. So if there is a state that you think is buggy, you can query the symbolic execution engine that tells you, no, there's no state, you don't have to worry about this, or there's no input for this, you don't have to worry about this. And it allows you to, in the sense that it does it systematically, it allows you to avoid the redundancies of, let's say, black box fuzzing and the blind spots of black box fuzzing, where with black box fuzzing, you just generate inputs that execute different parts of the code. You don't know that, you just generate inputs. And then you might always be executing the same parts of the code. The fuzzer might not be aware that there are other parts of the code that you can be executing. And with the symbolic execution engine, you know by construction that there is the left branch and the right branch, or the true and the false. And you will always be able to explore both of them. Well, modulo what resources you need, but that is for the rest of this presentation. All right. So let's take a look a bit at the, not say internals, but what makes up a symbolic execution engine. So you start with, let's say, a binary, which you've compiled already and stuff. And then the symbolic execution engine has to look at the instructions in that binary, disassemble them, and model them as some set of constraints later. So it looks at add RAX, RBX to RAX. So what this translates to later is that RAX equals RAX plus RBX. And the symbolic execution engine has to model all those instructions that it should know about, like the add, the subtract, the multiply, all those stuff, moving stuff around. And when you move stuff around, you're expected to have some memory, and then there comes the symbolic store, which says, okay, where is my memory? How is my memory represented? What is stored in my memory? Is it concrete values, symbolic values, variables, stuff like that? And then, yeah, as we said, there's the symbolic, the path constraints. So along the path that I'm currently exploring, what are the constraints that I have collected so far? So yeah, because the symbolic execution engine, I should come up with a Symex engine. Yeah. Yeah, because it explores all these different paths, it has to keep track of what each path has on it, so that it's meaningful, and that at the end it can do some queries or solve some expressions. So yeah, it has to find a way to store those constraints in an efficient manner, and that reduces, I don't know, space requirements, time requirements to solve it, and stuff like that. And then finally, you have to have the solver that basically allows you to solve these constraints that you've collected so far. And yeah, if the solver is not aware of some tokens in your constraint expression, yeah, so you have to also deal with unknown tokens. So what happens if the function is not defined symbolically as, or I could interpret it symbolically? What do I do then? And then also there's the states manager, which is keeping track of all these things. Each state has its own set of path constraints and own set of predecessors, successors, stuff like that. And one question with states always is there state explosion? Because yeah, you have all these ifs, you have 10 ifs, 10 if statements. That means you have 2 to the 10 states. And that grows exponentially with the number of if statements. You have a question?
What does SMT stand for?
Satisfiability modulo theorem. Some term that means solving expressions, or I'm not an expert on SMT, but yeah, I just use it as provided. So it usually involves defining the operations on like integers or booleans. What are the side effects of these things? Arrays, if you have arrays, how do you access an array? Let's say, what is the expression to access an array? How do you solve it? Stuff like that. So it has all these theories about different data types that symbolic execution engine usually have to deal with. So yeah, if you have floating points, like what is x plus y in terms of floating points, and how is it represented as a binary and stuff like that. You saw, okay, there's also like a bit vector theory, I think that's what it's called, where you saw in the assignment you have fixed size symbolic variables, which are like, you have 32 bits, for example, to represent a symbolic variable. So in addition to it being an integer, it also has the semantics of being a fixed size representation. So if it overflows, and maybe you have some signed or unsigned operations and stuff like that. So yeah, the SMT solver should be aware of all of these in order to solve the queries that you're trying to ask. But how it's implemented, not my area of expertise. Yeah. So for the example that we saw before, a symbolic execution engine would proceed as follows. It would start with, so here the state labels are the lines in code, and then it would execute the first line. It would add the constraints on x and y being 1 and 0, and then it checks the first branch. If it is not equal to 0, then it takes the true edge, and if it is equal to 0, it takes the false edge. And then it forks the state, right? So you have a state at 4, which is inside the then statement, and a state at 8, which is outside it. And within 4, you also have some more constraints. And then at 5, you have another fork. So if b equals 0, they take the true branch. Otherwise, take the false branch. And then here, the assertion works in these two cases. But what if a not equal to 0 and b equal to 0, and then you reach that? Is there a value that for a and b that violates the assertion at 8? And then the symbolic execution engine would tell you, yeah, there is a equals 2 and b equals 0. All right. So for some research stuff. So symbolic execution seems all nice and fine and ideal, but there's a lot of work happening in the background, and a lot of optimizations that are done, that are studied, and it's a hot research topic. Like, how do we solve these? And how do we leverage symbolic execution beyond just demos and just TA assignments and stuff like that? And through these research challenges, the hope is that you get a better idea of how symbolic execution works, and yeah, what are the different approaches for implementing it. So the main challenges are, as I mentioned before, is one of them is state explosion. So yeah, every time you branch, you have a fork, and that means the number of states you have is exponential in the number of branches you have in your program. So that can quickly lead to resource exhaustion. And basically, if you have too many states, then you cannot, you're exploring one state at a time, right? Because you're doing it, let's say, on a single thread. So at some point, you're exploring one state out of a million. So like, you're not doing any meaningful progress. Maybe you're exploring a state that doesn't lead you anywhere useful. Whereas you're interested, let's say, just in the one on the right here, but the rest are fine. So yeah, you have state explosion. Performance, of course. So ideally you would let the, let's say, symbolic execution engine run forever, but of course in production you don't have forever. So you have some timeouts, and then maybe you didn't achieve enough coverage before the timeout. So how can we increase the performance of the SymX engine? to do more with the limited time that you have. You also have imprecise analysis, and this is one of the main problems as well with symbolic execution, is that the constraints that you collect might not be very precise. So maybe you didn't model some instructions, or some new version of the ISA was released, and you're using an old implementation to interpret the new one. Maybe you just forgot to implement it. Maybe you just, another thing is that maybe you don't have a correct environment model. So usually, or like in an ideal sense, you have a program that is self-contained. It just has the code that you want to execute and symbolically reason about, and then you just go through it and then it's done. But most of the time, in production, that's not the case. You have programs that interact with each other, that interact with other environments. You have the operating system, you have the open files, you have the network, I/O, all of that stuff. You have external, external libraries. All of that stuff contributes to having an imprecise representation. Because if you want to symbolize all of these, it will take forever. But if you don't symbolize them, just make some assumptions about them, then that's going to lead to imprecise constraints that you've collected, and that leads to more false positives or false negatives based on how loose or strict you were in those estimations. And then, constraint solving. If you have a set of constraints, you want to solve them. If the program is too big, you might not be able to solve them, even if you manage to symbolically execute it. And that goes back to simplifying those constraints, and maybe you have some infeasible constraints that cannot be solved anyway, so you spend too much time on them for no reason. And so a symbolic or SymX engine has to deal with all of these stuff, and in addition, it has to deal with the disassembly and identifying function boundaries in the function, so that it knows what functions or what code to disassemble. Because at the end of the day, code can be anything, and you can't just it will probably result in confusing the symbolic execution engine if you treat all the data as code. So there's also function boundaries, and this is another a challenge. And but these two are not limited to symbolic execution, so that's why there's this border. What's more, the essence of symbolic execution is what's on the left, which is you have to process the program into these statements that you can model as constraints. You have the symbolic store. So how do you manage the data stored in that symbolic store? You have to model the environment, and you have your constraints and your states and all the stuff. It's a lot to deal with, and we're gonna explore some of these components and see what the researchers have done over the years to tackle these problems. So let's start with program processing. So the question here is, how is the SymX engine supposed to process the instructions contained in the target binary? So there are two classical approaches, either IR-based, which means intermediate representation based, or IR-less symbolic execution. So with IR-based, you take the disassembly or disassembled program, and you transform it into another language that the symbolic execution engine understands, which is in this case the IR that it understands. So with Anger, I think it's called VEX, if I'm not mistaken, VEX IR, and it has its own lifters that lift from, let's say, x86 or ARM or whatever into VEX. And so once it is in VEX, it has modeled all the instructions in VEX as constraints. So if you have an add, let's say, in VEX, then it knows that the destination is always equal to the source, or source 1 plus source 2, and that's it. Whereas in IR-less symbolic execution, you actually let the program execute as is, like with the x86 instructions that it is using. But then once you arrive at a branch or somewhere where you need to query this symbolic execution or the solver, there is where you do the reasoning. So if you have a branch, okay, I check what is the condition on the branch here, like it's a compare or whatever, and then okay, the compare should either be true or false, and then I make some assumptions about it being true, I make some assumptions about it being false, and then yeah, it's a bit less complete, but we'll see a bit about the comparison later between these two approaches. So in an IR-based symbolic execution model, yeah, you have the, let's say, x86 assembly, and then you translate it into this IR, and then this is what the symbolic executor understands, and then in an IR-less approach, you don't. The only thing that is executing is the assembly itself. And then there is some symbolic reasoning that is injected between or at the points of interest. So what are this is like a table showing the differences. So with IR-based symbolic execution, it is easier to implement because the number of instructions in the IR is usually smaller. So you just have to. So the two things you have to do are first implement the translation layer, which is from the ASM to the IR, and the second thing to do is model the IR instructions as a set of constraints. Whereas in IR-less symbolic execution, you have maybe thousands of instructions in the ASM, and then you have to model all of them, or yeah, it's going to be hard to implement. Another aspect of this is that IR-based is architecture agnostic, so you don't care what the binary was compiled in, if it's ARM, if it's x86, as long as your lifter or your translator supports it, then it should be fine. Whereas in the other one, yeah, it's dependent on the architecture, and that's by construction, right? You just made it understand x86 as an example, and then it's not portable. Another thing is because of the number of instructions and the complexity of the instructions, let's say, again, in x86, that is harder to solve the queries generated from the constraints collected. Whereas in IR-based symbolic execution, you just have some very simple instructions that are equivalent, let's say, to doing all these complex operations, but the queries that are generated are much easier. So it's easier or simpler for the solver to generate a solution. However, yeah, when you have the IR-based approach, if you fail to lift binary, or if the binary contains some instructions that you are not aware of, then you cannot continue. I mean, there are some ways to bypass this, but yeah, you cannot model an instruction, you lose constraints, and then what do you do in that case? Whereas in the IR-less symbolic execution, you have an unsupported instruction, you don't care, you just execute it, because that's what you're doing, you're executing concretely. Yeah, and then because of the layers, different layers of different layers that are injected in IR-based, it results in poor execution performance. Another thing is that you have a complex instruction in x86. What this usually results in is that it's translated into, let's say, 10 times the number of instructions in the IR. So suddenly you have 10 times more instructions to symbolically execute and collect the constraints for, and that results, this thing is on fire. That results in poor execution, and that is mainly, that's one of the main issues with symbolic execution, is that you don't have good performance. Like, you just try to run something as simple as the programs we gave you in the assignment, and then it just freezes forever. Whereas in IR, the symbolic execution, it's good because it runs on bare metal. But yeah, because of all the things we mentioned, IR base is likely under constraint because, yeah, it doesn't support some native instructions and modeling the environment and stuff like that. Whereas with IR-less symbolic execution, it's likely over constrained because you're executing essentially concretely, and you might have missed some constraints that were collected or that were supposed to be collected along the way. but you just queried some points of interest. So you constrained it along some parts of the path, which may have resulted in the constraints being more specific to your input rather than general along the paths of the program. All right. So let's talk a bit about state management. Any questions so far? Yeah.
So couldn't you avoid the instruction explosion problem by trying to have like a more decompilation-based approach, or try to like lift even further beyond just like register-based IRs? For example, like if you do symbolic execution on the C source code, you can often like get more useful results than if you did it on the binary. So maybe you could try to decompile up.
So there's, okay, so you're assuming that there is this also, let's say, IR squared level that is the, let's say, human readable language?
I think that's a pretty safe assumption.
Okay. So the first issue I see is that, yeah, with the compilation you also have issues. Like the compilation is also a very hard problem, and if you want to decompile code and then reason about that code, maybe you also lost some constraints or you added some constraints along the way, which makes it even more wrong or whatever. Yeah, even more imprecise. And the other thing is that, okay, you want to support, I mean, it's a valid, let's say, or it's a reasonable assumption. Like, yeah, if you want to support another level of IR, then you're saying that there's only this level of IR that I can reason about. So it's not going to be C, it's not going to be Python, it's going to be Vex human or whatever, you know. And then you just add another language to the whole list of languages that you can, you know, that exist in the world. I mean, maybe you can do it, but I feel like the decompilation process is going to bite you before you are able to reason about it correctly. And then, yeah, it is the inverse problem of compilers generating wrong machine code. It's like here you have machine code and you want to generate language from it, but then maybe you generate wrong language from it, and then reasoning about that language is wrong. It is already the case that with IR you might be losing something. So why do you want to do it twice? That's my concern.
Because like you'd increase the signal to noise ratio in terms of what you're executing.
But you're not getting, I mean, this is the same signal, right? Like you have your binary, and then you lift your binary to an IR, and then you lift your IR to a human readable language.
But for example, like let's say I have an extremely smart decompiler that realizes that an entire block of code is just this macro level simple function. Like it would be a lot simpler to like replace the entire block of code with just a simple thing that I can represent symbolically, for example.
Okay, that is another issue, which is simple functions. So the thing with IR-based approach, yeah, you have a small number of instructions, right? But if you say that my smart decompiler can make it even shorter, but then, or make the code shorter, because it knows that all of these instructions together make up a small or a simple function, then you have to tell your symbolic executor or your solver engine what the side effects of this simple function are. So you would have way too many simple functions. Like instead of modeling just add and move and whatever, you have to model also, let's say, CRC, or you have to model I don't know, some compression, you know. And then your symbolic executor has to know, okay, well now I have to support this extra function because my decompiler generated those that function call. So I either execute that function symbolically, which means I'm going back down because I don't know what that function does, or if I want to stay at that level, then I have to know what that function does as a set of constraints, right? So yeah, I mean, you're going back to the problem of, let's say, the IRless approach, or to some extent, because there you have complex instructions that have a constraint set that is, let's say, or you have just one instruction that does a lot of things. So that one instruction can be represented in a long constraint expression, Whereas you can model this one instruction as multiple instructions and collect constraints for those.
I mean, as an example, what would be very useful is like, let's say you have code that does cryptography. Like, often you have very high-level operations which involve a lot of bit twiddling, but represent a very concrete thing, which is actually amenable to like the SMT part. So, like for example, if I add 2 points on an elliptic curve, I have this huge amount of code to do it, but I can represent the fact that it's a group in the SMT solver and can reason about that.
Yeah, but exactly. But that means you have to tell your SMT solver how to reason about that. Whereas with the tools, I mean, you can of course do it. That's not. I'm not saying it's not possible to do. It's just harder to do. And then with the tools that you let's say you're working on the symbolic executor, now you suddenly have to also work on the SMT solver, and you also have to work on the compiler. And with the tools that you have, you just want to work on one thing, and then those tools don't allow you to do that. You're just gonna have to, flip the whole table. It's possible. It's just more complicated, and usually you tend to go for the simpler approach. Okay, I just want to deal with these 10 instructions and that's it. I don't care about everything else. But yeah, of course, different approaches. But that results in the this would not be very general, right? Like, what if you have other libraries that do different things? Do you want to also identify them? So what we'll see later in this presentation is there's something called function summaries, and you can sort of do what you're talking about, but not by adding theories to the SMT solver, just by telling it what are the side effects, or like what are the preconditions and what are the post conditions for this function. And then instead of actually symbolically executing the function, you just get the result. But yeah, I mean, it's less ideal than the approach you're suggesting, but the approach you're suggesting requires more work and might be less general. But good point. Okay. So yeah. So we talked about state explosion, and you have a lot of states. So how do you explore them, and how do you explore them efficiently in the given time budget? So yeah, the issues are you have too many states to track, state or path explosion. You might waste time analyzing useless paths. Let's say you have an error path, right? But the error goes through like a formatter and wants to print something. It also wants to log something on disk, and you have all this code that it's very neat for the programmer that did it, but for you as someone who's analyzing it, you don't care. You either want to tell the symbolic executor avoid it, or just simplify this. I don't care about this. So yeah, you might, because of all those states, you might end up wasting time analyzing those useless paths. And some states might have path constraints that are too complex and result in either slowing down your exploration or other issues, space requirements, stuff like that. So a few approaches are hybrid execution, which is, I don't know if you've heard of it, it's called concolic execution. Also dynamic symbolic execution. Also other stuff. Syncretic for some reason. There's program summarization, which is similar to the point we were discussing, that if you have some function that you know what it does, but you don't want to symbolically execute it every time, just tell the symbolic executor what it does, and then it will use that, let's say, cached version. And then finally, you have path scheduling. So yeah, selecting which paths you want to explore first and stuff like that. So first, let's talk about the hybrid execution. And what this means is that you mix concrete and symbolic inputs to support symbolic analysis and increase code coverage. What this essentially means, instead of starting from the entry point of the program, let's say, and symbolically executing from there, and all the paths, parsing the arguments, doing all the stuff that are done in main or whatever, you tell the symbolic executor, okay, take this specific path through the program, which is a concrete path. I give you the input to concretely execute it. Collect all the constraints along this path. Then once you reach a point, stop doing concrete execution and start doing symbolic execution. And what this results in, if you have, I'm not going to draw. If you have if you have some let's say argument parsing or some input parsing, and that you don't want to symbolically reason about, you don't care about it, you just care about reaching that point in the program, which is the function that you're interested in, let's say, then you just tell the symbolic executor, execute along that path, and then once you reach there, just explore. This might be similar to what you have done in the assignment, where, or what you will do in this, where you guide the symbolic executor along a certain path, and you tell it, okay, from there on explore. If you didn't do that, maybe you did other stuff, but that is one of the intended solutions. And yeah, this is what they call hybrid execution, where you mix concrete and symbolic constraints. And it is heavily used in fuzzers because it is more performant. Instead of having all those states you want to explore, you suddenly limit them to one path, and then at the end of that path you have all the states that you want to explore. That allows you to do like some directed fuzzing. So if you know where you want to fuzz, you just send it one of the fuzzer's inputs that reaches that target, and then solve symbolically to find other paths from that target. So yeah, the two approaches are concolic execution. DSE is dynamic symbolic execution, and the other one is syncretic. So with concolic, yeah, it's what I just described. You execute the program with symbolic and concrete inputs, collect path constraints, and use the concrete values to help symbolic execution get unstuck. So you reach some point, and then you reach some point through concrete values, and then you invoke the symbolic executor, and then there it tries to find a new solution or to find new paths. So in this case, you have this program that does something, and you just give it the inputs 1 and 2 for x and y, and then it does some math, and then it's like if it wants to do it symbolically, this is what it would do. It has these expressions. However, if it does it concretely, then it figures out that 1 is not equal, or like the check is false, so 1 is not equal to what? Anyway, 1 is not equal to 2 times 2 mod 50. But if it wants to, so this is what it executed concretely. It reached something. But in reality, you want to reach the error. So you flip the constraint. I thought I changed this slide. Ah, that's where I changed it. That's why. Okay. Well, there were 2 slides. Yeah. So yeah, you reach the false one through concrete execution, and then through symbolic execution on the constraints that you have collected, you say, okay, I want to flip the constraints now. What is x such that x equals 2 times 2 modulo 15, which allows you to satisfy the constraint on line 3 and then go to line 4. So with concrete concolic execution, you collect the constraints along the path S2, S3, S6. You reach the S6, you're not interested. Okay, let's flip the constraint at line S3, and this allows you to find a new input that satisfies the other edge, and then you go through the other edge. So yeah, you negate constraints, generate new inputs, cover new code. So the other one is syncretic symbolic execution. I don't know why they called it that. So it's basically the opposite. Instead of doing concrete then symbolic, you do symbolic and then concrete.
It's a pun.
I know. It's like it's symbolic.
No,
concrete?
syncretic means something that's characterized by being a combination of multiple things with an N.
Ah.
Put an M for symbolic.
Okay. Well, I saw it as syncrete, like instead of concolic, which is concrete and symbolic.
Oh.
Symbolic and concrete, syncrete, and then they wanted to make it rhyme. I don't know. Not not very interesting, but yeah. So you know where you want to explore. Again, like with concrete execution, you know where you want to explore, or concolic. So you start from the target, and given some notion of control flow in the program, you explore symbolically backwards. So from the target, you see which basic blocks, let's say, go to that target. So explore those basic blocks, and you do it in the inverse manner, you reach the top where you reach about where you reach the, let's say, the entry point, and then from there you try different concrete executions to see which ones you collected were true, or were reachable, or were valid, or stuff like that. So yeah, this the other approach, another approach in state management is program summarization. So you want to reduce the number of states that you have. You want to reduce the number of forks that you have in your state graph. So as your friend mentioned, you have a huge CRC function, some cryptography function, I don't know, and it does all that code. But in reality, what you care about is that it generates a 4-byte integer or whatever. So you can tell the symbolic executor, instead of analyzing the CRC function, depending or that implementation of the CRC function, just take it for granted that this is what it does, and then you just give it the expressions that summarize all that code. So yeah. Okay. So one example you mentioned is function summarization. Other examples are loop summarization. So another thing you might have seen in the assignment is that, maybe we'll take a break in a bit after we finish state management. Yeah, as you saw in the assignment, loops might get you stuck, and symbolic execution engines struggle with loops. So it is also of interest to maybe summarize the effect of loops and make it parametric on the number of iterations or something like that, so that you don't have to fork at the end of every loop based on the iterator. And then if the iterator is also symbolic, or the bounds are also symbolic, then you'll never finish, right? So that is also another interesting thing to explore. There's also state merging. Okay, wait. Yeah, I'm exploring. Okay. So yeah, the function summarization. Yeah, avoid paying the cost of re-executing the same functions over and over. And then there's a few papers on that if you're interested. So this one tackles summarizing functions with the preconditions and postconditions. The other one summarizes functions through lazy evaluation towards the target. So in a sense, it symbolically executes towards the target, but when there is a function call, it says, okay, I have the result of that function. I'll say that it is f of x, but I don't care what is the result. But in the end, if you reach the target, or on the way to the target, you depend on f of x, then you go and try to find the expression for f. Otherwise, you ignore it, and then you just go to your target. So basically, it's lazy evaluation. So this is the first one, which is preconditions and postconditions, where you look at this function, you analyze it, and then what this means is, with the precondition that x is greater than 0, the return value is 1, or with the precondition that x is less than or equal to 0, the return is 0, and then that's it. The symbolic executor now always has an expression for this function and doesn't have to analyze it every time. So with the loop summarization aspect, you also want to avoid paying the cost of the same loop every time state enters it. We also have some different papers discussing that. So one way is to look at the dependent variables within a loop, that, like, basically, if you have a sum that is growing, let's say you are adding the elements of the loop, then sum starts with 0, and then every time you iterate, sum plus equals to array of I. That means sum is dependent on previous values of sum, so you can try to analyze that and see that. And if there's no dependent variables in the loop, then that is similar to the loop unrolling or vectorization problems, where, okay, I don't care about the different iterations of the loop. They are independent, and then I can summarize the side effects of the loop for that one iteration. And that allows you to do some optimization in terms of the states generated or the constraints collected and stuff like that. Also some other papers collecting the side effects of the loop if the loop has a single path, and like a single path means there's no branching or if statements or anything, and another summarize multiple paths because it's better. Okay, all right. Okay, so we're talking about program summarization and how to reduce the number of states that the symbolic executor has to deal with. And another approach is to use state merging, which is to model state progression using path constraints rather than using new states. So instead of forking, you add a new type of constraint, which is like if then else, that says, okay, instead of forking, the new constraint is that x equals if then else, some condition, some true value, some false value. And this can be seen like here. You have the return value that depends. So this is the absolute function. If n is less than 0, then you return the negative or the inverse, whatever. And if it is not, then you just return n itself. So instead of forking there and having two states and having to explore in these states, you just represent the return value as an if then else. So ite here, then else. And then if n less than 0, then it's minus n. Otherwise, it's n. And then just like that, you merged your states, and then you reduce the number of states that you have to deal with. So yeah, there's also some related work on that. I won't go through much details on this. There's a support slide on that. But yeah, there's one paper leverages static symbolic execution to find opportunities of state merging during dynamic symbolic execution. So it does concolic execution until it finds that it is, let's say, stuck or it has a lot of states. So it uses traditional symbolic execution to find opportunities to merge the states in concolic execution. And then a couple more papers that, it finds more state merging opportunities, and then the next one makes it better. And then the last one is summarizing third-party libraries. So this is something also that you should have seen, or you will see in Anger, where let's say you're reading from an input or you're writing to an output, and in the case of the assignment it was writing to std out. So the printf function is summarized, or the putf function is summarized in a sense that it doesn't actually write anything to output. It says I'm writing to some buffer, and then you can query that buffer, and then so it doesn't go through printf or the implementation of printf. It just says, okay, printf writes something to the output buffer, and then I can model this as some side effect. Other way or other examples are like the cryptographic functions, stuff like that. You can summarize the side effects of those instead of actually symbolizing them. All right, and then in state management, there's also one last approach for efficiently exploring state, which is path scheduling. And what this means is you want to manage the exploration of paths to reach more interesting states in the program and avoid state explosion. And the two main approaches are pruning the paths, which means if you are exploring along some path and you determine that this path is not useful, then you just stop executing along it, and then you prune the end of you prune this path for the rest of the symbolic execution. And there's also path prioritization. So you select which paths you want to explore based on some criteria, and then, or you want to explore them now based on some criteria, and then you delay the exploration of some other paths. Also, a lot of papers. So preconditioned symbolic execution. So you constrain the program's input to promote exploration of exploitable paths, prune the rest. So you have some input. You say, I want only to explore along this path where the input has these constraints. So I don't care about all the other constraints. Similar to concolic execution in a sense, but it's not doing it concretely. It's just you add those constraints, let's say manually or through some analysis. under constraint symbolic execution is where you don't want to explore all the program. You're interested in exploring, let's say, some function in the program. So instead of exploring all the paths that lead to that function and all the different constraints along that path and whatever, you just give that function as an entry point, and then you leave all the unknowns as unconstrained or under constraint. So if you have a function that has global state, you say there's no constraints on the global state. This results in more, let's say, solutions, maybe more false positives, but allows you to quickly, let's say, explore these areas in your code which would otherwise have to be explored through a complete symbolic execution from the beginning until the end. So yeah, it's under constraint, but it can be very useful in detecting bugs and stuff in static analysis. And yeah, post condition, similar to precondition, but instead of the constraints being on the input, you constrain some states along the path or towards the end of the path. You say towards the end of the path, I want the flag, and I don't care what's in the beginning. So you say, okay, if a state doesn't have that, just throw it away. And then dynamic path pruning, which is when you're exploring symbolically, you have a state that forks, and you have the if statement, right? And the condition can either be true or false, and that condition depends on the input. Now, you can do one of two, or let's say three things. First one is check all. So every time you fork, you check, is it satisfiable or not? And if it is satisfiable, you keep it. If it's not satisfiable, then you just throw away the whole branch, right? So in this case, the 3 was not satisfiable, and then you just throw it away. You stop exploring there, and then the 4 was satisfiable, and then you continue exploring there. Now, what this incurs is a lot of calls to the SMT solver, and if your constraints are complex, then it might take a long time, or like on your critical path, which is the symbolic executor, you're always calling the SMT solver, and that means it's part of your critical path, and that might slow down your execution. So you might say, okay, I don't care, I'll just check nothing. So I'll explore the states, fork whatever, and then in the end, when I reach the target states, I'll check for sat and unsat. Well, that results in a lot of useless states. Like all of these that you explored, all of the time that you put into those states is now useless. You have also space requirements to store those states, and it's also a waste. So a dynamic strategy queries some oracle that says, okay, for this state, I might or might not check satisfiability, depending, let's say, on the complexity of the constraints or how much state I expect to be past that state or something like that. So yeah, it's not here, it's not very clear. We'll see a bit later where or what approaches have been done to answer this oracle question. Is this worth exploring or not? All right, and then that was for path pruning. And for path prioritization, so yeah, instead of so yeah, a couple, a few works have been done on that. This one picks the next state to explore to explore by walking the tree of already explored states from the root and randomly take branches until it. Just some strategy to explore the state graph, and you try to pick the state that covers unseen instructions. Yeah. There's directed symbolic execution, which is you want to study how to reach a specific point in the program, and then you try to, let's say, come up with some measures of am I getting closer to the target? And then if you are getting closer to the target, then you prioritize that state that is getting closer. If a state seems to be getting further from the target, then you deprioritize it. And then it is not I mean, it's not entirely correct, but it is a good approximation. Like if you have some measure of distance in the binary, and then a state seems to be deviating away, then you can deprioritize it. But of course, that state could eventually reach your target. But these are heuristics, and it might help. It's just, yeah. This is also used in fuzzing as well. So you also have chopped symbolic execution. This is similar to what we saw earlier regarding lazy evaluation. So you just say that there are some parts of the program that I don't want to execute, or I just want to skip them now, and if I need to, I will come back later to them. So yeah, like here, if your test function calls function A with a reference to X, then you say, okay, I will snapshot my state here. I'll come back to it later if I need it. But for now, I'll continue without constraints. And then in state 6, you have a reference to X that depends on a previous reference or previous value of X. So now you're like, okay, I need to see what function A did, because it took a reference to X and it might have changed the value of X. And then you propagate that change back to where you were. But if it doesn't, then you don't care, you just continue executing. And of course, if you add machine learning in your proposal, you'll get funding. So yeah, there's more machine learning stuff here. So use ML to decide which paths are more promising to reach a vulnerability, sure. And try to learn which paths are more likely, or yeah, more interesting. Offline training, whatever, I haven't gone into the details of those papers, and I'm not really interested. Okay, and then you have another component, which is the environment. So how do you handle code that interacts with external environment or third-party libraries? If you have unmodeled interactions, what do? Do you stop execution? Do you add a symbolic variable? Do you remove all the constraints? What do you do? Execute everything symbolically. Yeah. So there's two approaches as well. Either do abstract models, which is you model the effects of that interaction, or you do concrete delegation, which is when you don't know what to do, you just do concrete, and then you hope for the best. So yeah, in the abstract models, let's say it goes back to the same, let's say, idea of summarizing a call to an external procedure with a specific function. So either you do it at the function level or at the syscall level. So let's say your libc is the function level, and the syscall level is whatever happens inside the libc. So if you want to model printf, you can model it at the function level. You don't care what kind of syscalls it generates. Or if you want to model let's say the write syscall, then you can model that, and then you can execute printf symbolically until it reaches the write syscall, and then in your write you model the write as some symbolic expression, and then that would be the other part of the model. And then with concrete delegation, once you arrive at an external function or something that is unmodeled, you just delegate it to the real system and execute it with concrete values, and the returned value, you use it as a new constraint on your execution or on your state exploration and stuff like that. So yeah, one of the big papers in this is selective symbolic execution, also known as S2E. I think it was by some lab here. I forgot his name, George Candeya maybe. It does this basically. It interleaves the symbolic and concrete execution based on external interactions. But it does the entire software stack. So there can be no unmodeled interactions. The whole thing runs inside S2E. So it models the entire environment basically, and some parts it executes concretely, some parts executes symbolically, and yeah. Some other work. Unleashing mayhem on binary code. Okay. And then also interleaving concrete and symbolic execution. Basically, this is the concrete delegation solution. Now, constraint management. So, while exploring, you have a lot of these branches and a lot of these operations, and then you have a lot of constraints. So, can we exploit some opportunity for reducing those constraints, make our SMT solver solve them faster? Can we remove some useless constraints, some duplicate constraints, stuff like that? How do we efficiently solve these? And then also there's some related work on that. So yeah, in the check all strategy, querying the SMT solver too often is a bottleneck, and maybe some constraints cannot even be solved because maybe you didn't model some operation, or it is also unsatisfiable. So you spend so much time, and then eventually what the solver says it's unsat. So you just wasted so much time just to get an unsat solution. So yeah, also some approaches in reducing those constraints. So you simplify the constraints with equivalents to speed up solving time. Is there examples on this? Yeah, so these works. So expression rewriting. So instead of x plus 0, so instead of every time dealing with the plus, you just say it's x. And instead of x times 2 to the n, it's just a shift left by n. And then 2x minus x, you simplify it, it's just x. Constraint set simplification. Then if you have this constraint, then it just always, what? X greater than 5 and x equals 5? Sorry, x greater than 10 and x equals 5. Oh, I don't know. I feel like this should be false. But anyway. Yeah, you have, okay, implied value concretization. So you have this expression for, or equation for x, and then instead of always using this constraint x plus 1 equals 10, you just say x is 9, or you solve this equation. Let's say x is 9, then everywhere that x occurs, it will always be 9. And then constraint independence. If you have some constraint set and you want to query some expression, if the constraint or if the expression doesn't depend on all the things in the constraint set, you can reduce your constraint set. You can remove the k because there is no dependence between I and k. So you also reduce the number of constraints you pass to the solver. You can also cache constraints. Yeah, caching always a solution for everything. Yeah. More ML, you can try to predict. Wait, is that here? Yeah, it is here. Yeah, whatever. Canonize, vectorize a set of constraints and their solutions to train a deep neural network. Use deep neural network to check for satisfiability. Sure. Also more ML, but this is, I mean, sure. But what I wanted to point out here is that this can be used similar in the check dynamic we solved for. If it can predict how long it's going to take to solve a specific set of constraints, then you can say, okay, now I want to solve the constraints. Now I don't want to solve the constraints. I just want to explore without checking, and that might help you, you know, schedule your states or prune your paths more efficiently. Better constraint solving techniques, some more math involved, and some heuristic approaches. So instead of finding the optimal solution or finding a solution in one iteration, you do some meta-heuristic search like taboo, then you find a solution through that search. Yeah. There's also a paper on fuzzing the constraint set. So if you have a set of constraints like that, you have the function that whatever, you have some assertions. Instead of querying the solver, you translate this into a C program, and then you fuzz this program. And then if it reaches the end through some solution, then you found a solution for this. Yeah, use ML to predict what is the best solver to handle a specific set of constraints and apply the decision at runtime. Yeah, you might have different solvers that each are what's the word? What? That each are specialized in some type of constraints. Let's say we have the float operations, or you have the integer operations, you have array operations. Maybe each solver has different properties, and then you at runtime you can decide which one you want to use, or maybe one is better than the other for some type of operations, whatever. Another one interesting aspect is store management, which is basically how do you store your symbolic variables in memory. You might think that for every address you say it's a symbolic variable in memory, or every byte in the every byte in memory is a symbolic variable, and then you add constraints on that. But then that results in a just a naive implementation of that can be very inefficient, or very slow, or very space-wise. It takes a lot of space. So what are the approaches for that? So one approach is called single concretization. Instead of storing the symbolic variables, you just store a solution for that variable. So here you query the solver, what is a value of RBX, and then you store in RBX just deadbeef, and then you continue on, and then REX is just the memory at deadbeef. The forking model is, okay, it's like the single concretization, but I concretize multiple times, and then for each of those I fork a state. So if it is the first one, then RBX has this, and then REX has the value at that address, and then for each value of RBX you do that exploration. There's the merge model, which is slightly similar. Instead of forking, you say, okay, the expression of REX is an if then else, like the merge that we saw before. So if RBX, or if x0 equals something, then REX equals mem of something. If RBX equals something else, then REX equals mem of something else. And then finally, I think what is the most common, or the one at least I've been more familiar with, is the flat model, and using the SNT array theory, which is it allows you to reason about arrays and the contiguous areas in memory, and how to index and select values in those arrays. And then RBX is a symbolic value or variable, and then REX is the memory array, which is the whole thing, as a symbolic variable. You select the index, which is XU. Right? I think this is what Anger implements, if I'm not mistaken. The other ones might be faster or something, but might be less complete, because they're concretizing, and then you don't have all the solutions, you just have some solutions, and you might lose some constraints in that process. Okay. So more work on that, and how to manage the store and stuff. Using the merge memory model. Is there an explanation on this? No. Okay, whatever. If you're interested, you can look into these. They're just not very necessary it's just to give you an idea of what are the different components in symbolic execution and how people have tackled them. So in this model, I think there was some. I removed it, I think. There's this mem thing, rethinking pointer reasoning in symbolic execution. Instead of using like the merge model, it uses a flat model with some merge expressions. So it uses the flat model as in it uses the array, but when you want to find when you want to access an address, it uses the merge based on some expressions it had collected earlier. Not entirely sure, but okay. This one I found a bit interesting. A segmented memory model for symbolic execution. So it splits the memory into some segments, and I'll show you in this example. So in the flat memory model, you have this memory as one array, and then if you want to get some concrete solutions for the pointer, all of them fall within this big array. And this can result in, like, if you want to, if you have, let's say, if you have an array, like not this memory array, if you have a buffer in memory that has some size, okay? And you want to access that buffer with a symbolic index, then that symbolic index might be able to span all of memory. And that, like, if you want to do some reasoning about that index, then you will have to do the reasoning over all of memory. Whereas if you split your memory into segments, then you say, okay, my symbolic index in the first case has to be between this value and this value. And if it is not between this value and this value, then you take the other case. And then it is between C and D. And if it is not between C and D, then it's between E and F. And then when you want to do your reasoning, you do over just one segment of memory, not all of memory. And then that might allow you to have simpler constraints over the memory array that you have. Instead of having constraints over the whole memory, you have some partial constraints at first, which is the buffer does not span, or the index is not outside of the bounds of this segment. And then in addition to those constraints, you're like, okay, I'm dealing with this segment only. So all of your constraints might now just apply to this segment rather than all the segments in memory, or all of memory. Found this a bit interesting, but yeah. And then, yeah, relocatable addressing just combines previous approaches into one, I guess, approach. Okay, I think we're finishing earlier. Sorry for, yeah. So not at 1, maybe at 12. So yeah, just rushed through all the related work. It's nothing very critical to know. I haven't personally read them all. I've seen the ones that are interesting, and it's just good to understand the different components of symbolic execution, what goes into making the symbolic execution engine, what are the challenges, how people have tackled them, stuff like that. So yeah, the current state of research pushed the boundaries of the design of original symbolic executors, but the research is very fragmented. Each one does their own thing. They're not compatible. They're not Anger works on Python, uses the VEX IR. CLE works on the LLVM IR. It doesn't even, the model is a bit different. So you compile your code into an LLVM intermediate language, and then you invoke CLE, and it's a bit more hands-on rather than Anger. You just tell it, okay, explore, and then you cannot really combine the two. They're just different engines. S2E is also another one, and then the point that they're trying to make here is that we cannot really combine all the results that we've gotten from the different research projects. The quality of tools is debatable. No real incentive for improving it, because you have old versions you cannot compare against. You don't have fair comparisons because each one is using a different language or using different models of memory, using different SMT solvers. There's also conflicts between symbolic execution techniques in different research areas, and they are not very well understood. But the optimistic side of that is that there's lots of room for improvement, and if you're interested, you can work on those and be better than everyone. What we've explored are the fundamental ideas in modern symbolic executions. State management, you have concolic execution, efficient state merging, path pruning, flexible search strategies, function summarization, caching of constraints. You can this I didn't mention maybe, but anyway, binary processing. You can instead of doing vex IR or any type of IR representation, you can do it inside like QEMU and then do dynamic binary translation to. Yeah, this is similar to the IR-less approach, but I think here it's binary. It's hybrid, so they do both. I don't know. And then, yeah, there's the aspect of constraint solving. You want to reduce your number of constraints. You want to cache the constraints that you've solved. You want a solver that can do all the constraints, which is, in the case, I think the ML approach for finding the best solver, stuff like that. With environment modeling, you have concrete delegation if you fail or you do abstract models. With store management, you have like using array theory. We talked about the flat representation, the merge model, the fork model, the single concretization. But yeah, yeah, and this is it. The rest is just references. So yeah, this is the slide for today. I actually finished quite on time, I think. Any questions? This was an information dump, but what you get, what you should, I hope, get from this presentation is just the different challenges in symbolic execution. It's not this black box that you run anger and it just magically does it. There's a lot of things that are being done in the background. There's a lot of assumptions being made. There's a lot of heuristics maybe. So it is a nice, hypothetically it's a nice thing. In reality there's a lot of hackiness going on in the background, but it's still a useful tool, especially if you use it right. And later in life you're working on a project and you think that symbolic execution is useful for you. You don't just have to use what is given to you. You can modify it, you can tweak it to your requirements, and then you can actually have a powerful tool at your hand to solve your problems. And then hopefully with this presentation you know what kind of engineering has to go into that and what kind of aspects of the symbolic execution you need to take into account when working on this. Yeah. All right, if there's no questions, we can end the session early today. I'll stop recording.